common multiparticle motion situation arises when two or more objects collide. We often picture in our minds that colliding objects make contact, for example, like a case where two automobiles crash. However, contact is not necessary for a collision. For example, when an electron collides with an atom, there typically isn't any contact. The key features of a collision are strong interactions between the objects during a relatively brief time interval. It's possible to have strong interactions during brief time intervals for both contact interactions, as in the auto crash example, or action at a distance interactions, such as electric interactions in the colliding electron-atom case. In all cases involving collisions, the multiparticle form of Newton's second law, or equivalently, the multiparticle momentum principle, as your textbook calls it, provides a very good starting point to make progress on understanding what's going on. Let's first consider a head-on collision where all the action happens along only one spatial dimension. Here's the situation. Object 1 has mass m1 and initial momentum p1 initial, as shown, just before it strikes object 2, which has mass m2. Just before the collision, object 2 has an initial momentum p2 initial, as shown. After the collision, object 1 is observed to have final momentum p1f, as shown. What is the momentum of object 2 after the collision? We'll start with our fundamental principle, Newton's second law, expressed in terms of momentum, and choose to apply this to the system containing both particles. Here, the momentum vector p is the system momentum, which, as we discussed earlier, is the sum of the momenta of all the particles in our system. Now, we make this choice of system because the interactions between the colliding particles are typically much stronger than the interactions between the particles and other agents in the surroundings. This means that, in effect, before, during, and after the collision, the net interactions with the surroundings, expressed as F net, are effectively zero. So Newton's second law says here that the time rate of change of the momentum, dp dt, is zero. Or, equivalently, the system momentum vector p, p1 plus p2, is not changing in time. Or, as we often say, the system momentum is conserved. Note that the momentum of an individual particle can change. However, the total momentum must remain constant. That's the key idea here that will allow us to solve for unknown quantities. So let's do that. Let's find the unknown here, the final momentum of object 2, object 2's momentum after the collision. Since the system momentum is conserved, it must be true that the initial system momentum, the system momentum before the collision, is equal to the final system momentum, the system momentum after the collision. So let's write that out. Now we see we know everything here except for our unknown, the final momentum of object 2, p2f. So let's solve for that and plug in the numerical values. And so here's the result. Now we can learn more about this problem by applying our other fundamental principle, the energy principle, to this problem. We discussed earlier that the interactions of the multiparticle system with the surroundings are typically negligible compared to the interactions inside the system. So if we apply that same assumption here in the energy principle, we know that, effectively, that the energy transfers to and from the surroundings, the right-hand side of the energy principle, are effectively zero. So we have the change in the total system energy, delta E, for this multiparticle system must be zero. Or, equivalently, the total energy E is constant. Or to say it another way, the total energy E of the system is conserved. There could still be energy changes in the system. However, the sum of all energy changes must add to zero. If one type of energy, say, decreases, then at least one other type of energy must increase. Let's check for energy changes in this example. We know that we have kinetic energy in the system, so let's look at delta K, the change in the system's kinetic energy. The system kinetic energy is just equal to the sum of the kinetic energies of the objects. The most familiar form for each object's kinetic energy is 1/2 times the mass of the object times the speed of the object squared. However, we know kinetic energies can be found directly from the magnitudes of the object's momenta, like this. So let's do that. First, we find the initial kinetic energy of the system, then the final kinetic energy, and now let's find delta K, the final kinetic energy minus the initial kinetic energy for the system. And we see that delta K, the change in kinetic energy, is negative. This means our energy principle for this case must have at least one more non-zero change in an energy in the system, typically a change in some internal energy of the multiparticle system. Collisions with this character, where the kinetic energy before the collision is not the same as the kinetic energy after the collision, such collisions are called inelastic. One common internal energy change that happens for inelastic collisions is a change in thermal energy. So, if that's the case here, the energy principle would be written like this, and we would say that the decrease in kinetic energy as a result of the collisions would show up as an increase in thermal energy of one or both of the objects. There would be a temperature change, a temperature increase, resulting from the collision. Other types of internal energy changes would be possible in an inelastic collision, say changes in the rotational or vibrational energies of the objects. Exactly which internal energy changes are involved would depend on the specifics of the collision under study. Now, it might happen that the collision does not result in a kinetic energy change. If that's the case, the collision is called elastic. Here's an example. Object 1 has mass m1 and initial momentum p1 initial as shown, just before it strikes Object 2, which has mass m2 as shown. Just before the collision, Object 2 has an initial momentum p2 initial as shown. After the collision, Object 1 is observed to have final momentum p1f as shown. What is the final momentum of Object 2, the momentum of Object 2 after the collision? And is this collision elastic or inelastic? The wording of this problem looks almost identical to the problem we solved earlier, and we can find the final momentum for Object 2 in just the same manner. To find that, we apply conservation of momentum as we just did. We won't work this out in detail, but here is what we find for the final momentum of Object 2. See if you can get this result. Now, to determine whether the collision is elastic or inelastic, perform the same test as we did before. Compute the initial kinetic energy and the final kinetic energy, and then find the change in kinetic energy, K final minus K initial. You should be able to show that the kinetic energy has this value both before and after the collision. So the energy principle here would say that delta E, the change in the total system energy, would be equal to delta K, the change in the system's kinetic energy, which is just going to be equal to 0, which is typical for an elastic collision. Now, in this lecture, we discussed head-on collisions, collisions in just one spatial dimension. Next, we'll discuss an example of glancing collisions where we apply multiparticle Newton's second law in more than one spatial dimension. We'll do that in our next lecture.